So in this previous section, we looked at regularization. Regularization was a way to restrain the model. We did that by creating an overfitting penalty, which looked at restraining the model to have for small values for the weights in the model. This is used at unseen test points that would wildly vary from what they might look like in the test cases, which might be more smooth. In this second half, reality check, we're estimating the test cost directly. How do we do that? Well, let's take a look. Let's pretend that we can draw a new point from the test distribution, which should be the same as the training distribution. We're going to pull this test point out, x, y, and note its cost. It's going to be a unit cost in the case of binary error, either 0 or 1, or some squared error cost if we're talking about regression. Again, the predicted value subtracted by its actual value and any distance from there squared. In binary error, we just need to know whether it matches or not. If it doesn't match, there's a cost of 1, and if it matches, it's 0. Let's take a look at how good the single point estimate is at predicting the test cost. Well, let's take a look at the expected value of a single point estimate. Well, if we draw it from the same distribution, we could get any point in our X space, and therefore averaged over all of the points with the same probability distribution as the training data, we would just get the same thing as our testing cost. So we can see this is an unbiased estimator of the true testing cost. But because it's just a pointwise estimate, our variance is going to be, we don't know exactly how much the variation is going to be, and we can just give it a unit cost of sigma squared. Depends on how bad the estimate it is. For example, in the univariate case where I take a point x and I measure it, I don't know whether that measurement is too high or too low. All I know is that the samples are going to be centered around the true mean, but I could be getting any value. If I get a value fairly far off from the mean, my estimate of the test cost is going to be pretty bad. If I'm lucky enough and I sample a point pretty close to the mean of the test cost, then we have a good result and we can accurately estimate the test cost. The problem is we have no idea which point we're going to draw, so we're going to get quite a lot of variance here, which is the killer problem. From this idea, it's pretty clear that we don't want to use a single point to estimate the actual test cost. Can we do better? Of course we can. Why use a single point? We could use more than one point. Let's say we get a collection of points instead of a single one. Is that going to help us estimate our costs better? Let's see. We're going to get the idea of a validation set rather than a validation point. By a validation set, we're going to say that we have more than one point, up to a total number of k points. These should be capital Ks. Sorry about that. When we use each of these independently drawn k points, our validation cost, or J-val, is going to just be, again, an average, the point-wise cost for each of the individual points. Let's see how that does in terms of our estimation, again, for the expected value in the variance. For the expected value of the validation cost, we have again our average of the pointwise costs for each of the k independently drawn points. Of course, since the expectation of the individual points is the same as our expected test costs, there's no difference here. We get the same value back. It's just being summed and divided over as an average, but we'll actually end up with the same results. So no difference there. Okay, so that didn't seem to help very much, but it didn't hurt either. How about going to have k points for the variance? Will that help? Well, let's take a look. In the variance, for calculating the variance of the test cost over the validation set, we're going to have the validation of individual points again. The cost of individual points variance is actually a little bit different because we're going to have a double summation here, which we can draw out. We're drawing on the whole k points. And each of these k points is going to have its own correlation values on the diagonals. We're also going to have cross-correlation values for all of the off-diagonal cases, and likewise on this other side. However, note, because the points were drawn independently, this means all of the cross-correlation terms are going to be zero because they're all independent. In the end, we only have to sum over the 1 through k terms on the diagonal. But because the correlation matrix itself had k-squared entries, we get the extra bonus of being able to divide through by another factor of k. You can see the benefit that this has because we can compare it versus the pointwise estimate of just having sigma squared. We get to divide through by the number of validation points that are in our validation set. This is consistently the same reason why we would use a larger set to get a better estimate of a value. At the end of this, we can see our validation error has this benefit of being able to change its unbiased estimate of the test error with proportion to the square root of the number of points that are given. This is just undoing the square that we have over here. So where do we get these points from anyways? Well, the only place we can get them is from our training data set, since we're not allowed to look at the testing data set. So what we're going to do is we're going to subdivide our training data set into two parts. We're going to take one part and use it for the estimate of our test costs. And we're going to use the other part, the m minus k points, for the actual training of the algorithm that we're going to then evaluate using the validation set. So we need to set our k. How do we set it? Well, if we use a small k, like 1 point, like we did for the pointwise estimate, you can see we're going to get a bad estimate because our variance is going to be high. So, should we use a large k for validation? Obviously so, right? We'll get a better estimate. The bigger the k, the better. Are there any difficulties when we use a large k? Think about it for a second before we go on. Hopefully it's clear to you if we have m as the limit of points that we can use as we push back k. As we take a larger and larger k, we are going in this direction. Let's say we set k to a very large number, then our training performance is going to be pretty terrible, and we can expect our training error to be really through the roof because we don't have enough points to estimate a good model fit, even though our measurement of the test cost will be fairly accurate. So there's some give and take here too. There's a trade-off between having large k and small k. We're going to try to use k but put it back into our total data set. How do we do this? We're going to first take our training data set and subdivide it into two parts. We're going to subdivide one part into train. This is like the training part of the training data set. And we're going to use that to train our learning algorithm to yield out a hypothesis. We're going to call this hypothesis H minus, just to denote that we took out some points. Then we're going to test the hypothesis to see how accurate it was. We're going to use it on the validation data set, which it didn't have access to when we were training it, to yield a cost estimate for the validation. This is going to give us the estimation of the test cost of this hypothesis, with the added benefit of being able to divide through by a factor of k in terms of our variance, getting a more accurate estimate of our test cost. So that was step 2 and 3. In the end, what we do is we now have the correct value for our test cost using the H minus hypothesis. But we rather, of course, use the entire data set to return a best hypothesis as possible. So we'll train using all of the data points and return this at the end for use. So we want to use a large K where possible. If we don't use a large K, our H minus will be trained on too few examples, and it will lead us to a poor estimate of the actual hypothesis. A good rule of thumb that we'll look towards is using a K that's about 20% of our full data. This means our training data set will be 80% of the data, and our validation data set will be about 20%. And note, this is after we have split it into training and a test set, which we cannot see at all. Here, let's take a look at the expected validation error for the class of quadratic lines, where we have a total of 40 data points to estimate a 10th order polynomial with a significant amount of noise of 0.4. You can see how the blue line goes about as we slide the validation set from 0 points or a single point-wise estimate all the way up to about size 30, where we're using 75% of the data for validation and only 10 points for model estimation. What's going on at both ends of this graph? Well, when we have too many points for estimation, our cost goes up. But why does our cost go up? It's because our model is not trained with sufficient amounts of data. As we increase the amount of data that we train with, the cost goes down because our model is getting more accurate. Continues to go down all the way here. However, our estimates of the actual validation costs start to vary, starting perhaps around this point, where we can see the gray tube gets fatter and fatter. This is because now we have fewer and fewer points in our validation set, and our estimates of the validation costs become more and more inaccurate.